All right, so problem number 4, we'll be drawing a shear and moment diagram. It's going to be, I hope you think it's a pretty simplified shear and moment diagram. I'm even going to give you the statics. I'm trying to kind of isolate your ability to draw shear and moments. So I'm going ahead and giving you the statics, even though I think you could figure this out, right? If you sum the forces in Y of the whole free body diagram and sum the moments about A of the whole free body diagram, you would get this By is 10 kilonewtons up, and you would get that this AY is down 2 kilonewtons down. So, but I'm going to give that to you in the problem statement, so you don't have to do it. Be able to do these distributed loads, right? Distributed loads, right? You can replace that distributed load. We'll talk about how you need to use that. That's equivalent to an 8 kilonewton force, right? Be able to do triangular distributed loads. All right, be able to do triangular distributed loads. I will not make you do these distributed loads that go from one height to another, but uniform and triangular distributed loads, be ready for those. Okay, anyway. Let me leave that. Okay. For the shear diagram, I'm just looking at forces and distributed loads. For shear diagrams, I'm just looking at forces and distributed loads, and it literally just pushes my shear diagram up or down. So here's my shear diagram. Start at 0, and then immediately what happens? I get pushed down by 2, so draw me that -2 right there. All right, then what is happening in between here? Are there any forces? Are there any distributed loads? No. So it stays at what it was at, okay? So it still is at -2. Then what happens? An immediate 10, so I get pushed up to 8, and then it hits the distributed load. So first I figure out, okay, what is the area of that distributed load? It was 8, and so it gets pushed down by 8, so it goes from 8 to 0. Hey, that's a good sign. We should always end up at 0. How did it get pushed down? Did it go down like this? Did it go like this, straight? Well, just it gets pushed down by a uniform 4 kilonewtons per meter. So for every meter it is going down 4, it has a slope of -4, of down 4. A uniform distributed load pushes this down linearly, right? A uniform distributed load pushes this down linearly. A triangular distributed load would push this down harder on the towards the end than it did from the beginning. A triangular distributed load this way would push it down more like that, right? It gets pushed down harder at the beginning than at the end. So be able to do those triangular distributed loads, but for uniform distributed loads, it becomes a linear pushing down right there. And you should get back to 0. If you get back to 0, that's a good indication that you did everything right. All right, so there's my shear diagram. That's it. All right, now my moment diagram. 3 things I'm thinking about for my moment diagram. I'm looking at just moments that are drawn on there. Or maybe if this was a wall and there was a moment drawn on there, and I think let me try to tell you this right. Clockwise pushes it down. No, I need to tell you this correctly. Clockwise moments push this up. All right, clockwise moments push this up. All right, but there are no moments drawn on here. So number 1 that I'm looking for are moments, couple moments, concentrated moments drawn on there. No, 2 is the area under V diagram. 2 is the area under the V diagram. And then 3 is V is the slope of M. That tells me what type of curvature my moment diagram needs. Okay, so I don't have any of these. I'm looking for the area under the V. So here, I see a good, nice rectangular area under the V. So the delta M would be the area under the V. 2 by 4, this would be 8. And you can think of it as, oh, that's -2, so I can say -2, so it'd be -8. Or just say areas below this axis are negative areas. Areas above this axis, like green, that would be positive. So this is below that axis. It's a -8, so it goes from 0 to, draw this in pink, 0 to -8. Now, did it get there this way, this way, this way? Well, I think V is the slope of M, so -2 is the slope of M. -2 is the slope, -2 is the slope, -2. It has a constant slope of -2, and so it would be linear. That should be linear. And if, you know, use a credit card, use a ruler, use something to indicate that it's linear, or you can write on here linear. Just let me know, because sometimes it looks a little bit curved to me. That is linear. Very similarly, a uniform distributed load leads to a linear shear. A uniform V leads to a linear, right? It's because these are the integrals of each one. Okay. All right. Then I've got that area. That's a positive area because it's above this axis. What would the area of this be? What is the area of a triangle? 1/2 base times height. This would be 8. Positive 8. Oh, yes. Great. And, you know, that's I got back to 0. That's good. That's what should have happened. Now, does it go linear again? Does it go this way? Does it go this way? Well, V is the slope of M. So this one has a slope of +8 to begin with, then 7, then 6, then 5, then 4, then 3, then 2, then 1, then 0. It ends with a slope of 0. So it starts with a positive slope. It ends with a smaller slope. Do you see why this would be curved that way? This would be curved that way, right there. And, you know, you could exaggerate it for me to make sure you know. You could say curved. I like to call that concave down, but just make sure that you know, that I know, that that is curved. And that's it. I want you to label all the important points, right? So this is the only point you have to label is that -8, right? And then say, make sure this is linear, this is curved. Okay? All right, so since this is not a real mechanics of materials class, I'm not going to give you a tough shear moment diagram. And I'm going to give you the statics. And so you just have to draw the V, draw the M, be able to handle distributed loads, be able to handle triangular distributed loads. Yeah, but you see that it goes from nothing to uniform to linear. It goes from uniform to linear to squared. You know, it's the integral. V is the integral of the loading, M is the integral of V. All right, you have a lot of example 1 of these to look at. Now, a few things you don't have to worry about that I do in my mechanics class. A lot of times I have some where the V diagram goes from here to here. Whoops, sorry, the shear, if the shear goes from here to here and it crosses 0, you would have to find out where it crosses 0 in order to find that positive area and that negative area. I'm not going to make you do that. I'm not going to make you do one that crosses 0. Don't worry too much about that. I'm not going to have you calculate the area. Well, let's talk about that real quickly. The area of a squared, triangular shape. So if this was a, let's think about this. If this was a triangular distributed load right here, then the V diagram might look like this. And you might want to find the area of that V diagram. The area of that V diagram is 1/3 base times height. If it either starts or ends with a, zero slope, then the area is 1/3 base times height. So yeah, you might need that to go from there to there. If this was this triangular load and it goes like this, right? If my V diagram goes from here to here, that area would be 2/3. 2/3 base times height. So anyway, yeah, do be able to handle triangular distributed loads. Look through some problems where we did triangular distributed loads, please.